Okay, so Admin Code Day 22. I did record something immediately at midnight, but for some reason it didn't pick up what I was doing in my code, so it seemed like kind of pointless to try to put that on YouTube. So instead, I'm just going to walk you through the solution. So first, we've just got, well, let's talk about the problem for a second first. So for the problem, we've got combat and then recursive combat. So combat is the card game War, where players 1 and 2, they deal out the top card from their deck, and whoever wins takes those two cards and puts them on the bottom of their deck. And we're simulating war, and then uh, printing out, a specific number that corresponds to the solution. So let's take a look at my solution for that part one. So I first copy the decks just so that I don't mess with the originals. And then I say, while each deck is not empty, we grab the two top values. If the player one has the bigger value, then sorry, one quick clarification I want to make. I have these in reverse order, so the last element is the one that's on top of the deck because dot pop was easiest for me to use. So in this case, what we're doing, to put it on the bottom of the deck, we put it at the very beginning, and the specification said that the winning card should be on top of the losing card. So in this case, top P1 beat top P2, so this is on top of this one because it's later in the list, and then we append, and then we add it to the rest of the deck, leaving the stuff on top the same. And then the same happens with if player 2 wins, except for on player 2's deck. And then what we do is we just return the score at the end. So the deck score is calculated by iterating through the deck, and each element in the deck, the last card in the deck is worth 1 times its value, the second to last is worth 2 times its value, third to last is worth 3 times value. It's convenient that I have mine reversed in this case because now I can just iterate through and I don't have to do any sort of subtraction. I just know that the last element is the first element in my deck. So that lends itself well to this little function here that just returns the deck score. So that's all well and good. And going into part two, I made a little function called recursive combat. So recursive combat is interesting because now we have this weird case where if both players have at least as many cards remaining in their deck as the value of the card they just drew, the winner of the round is determined by playing a new game of recursive combat. So it's aptly named, I would say. So let's take a look at what we have to do in this case. So first of all, we set up this. Let me remove these print statements because I don't need those anymore. Whoops, 1 second. Just making sure that my thing's actually running. There we go. That's what we want. Cool. So we copy our decks, and then we initialize this thing called prev states, which is essentially just a set containing every single game state that's ever occurred, because we need to handle a case here, which is essentially if both players' decks are in the exact same state as some time that happened in the past, player one wins immediately. And so the simple thing to do here is to just have a set full of tuples, because tuples checking equality is nice and simple, and they're hashable. So we can just drop these tuples, this pair of tuples, which represents the game state in its entirety, the player one deck and player two deck. So we initialize this previous states to empty, and then we just run until something causes it to end. So the first way it can end is if player one runs out of cards, in which case player two win, which I'm representing by false. And if player two won, then we return the deck score of player two's deck. Similarly, if player two loses, the player two runs out of cards, then we return true, meaning player one won, and we return the deck score of player one. And then we check to see if this game state is a repeat. If it is a repeat, then player one wins, meaning true, and we return player one's deck score. Great. And then if we didn't hit any of these cases, then this is a new valid state, and we add this to prev states, and we keep going. So this should look familiar. It's the exact same thing as the other version of the game. We pop off the top card of each deck, and this winner value is just saying, did player one win this round, or did player two win this round? And if it's true, player one won the round. If it's false, then player one won the round, or player two won the round. Sorry, let me say that again. True means player one won. False means player two won. So there's two cases here, one of which is when we can enter this fun little recursive case, which essentially just says, hey, does player one have enough cards left in their deck to do this recursive case, and does player two also have enough cards? If so, we call recursive combat on the so we need to get all of the cards on top of the deck, excluding the card we just popped off, and that's easy because we've already popped it off. And we need to get top P1 cards off the top of the deck. So this is done by taking negative top P1 through the end with this fun little Python syntax, and the same thing with player two. I had a lovely bug where I accidentally subtracted one here, and that caused it to fail. And I also had this, instead of just going to the end, going to -1, which cuts off the last element of the list, which is also bad. So there were a couple little off by one errors that really slowed down my part too. So yeah, if we get this case, then we do the recursive thing, and then the winner is returned because we've decided that returning true means player 1 won, returning false means player 2 won, and so that gets fed into this winner variable here. Otherwise, we do the same thing that we did in the regular combat, where we say, oh, if top P1 is bigger than player 1 won, and we say true, otherwise false. And then we do the same thing as in the other game, where we smack on the top cards, what used to be the top cards, to the bottom of the deck, which is the beginning of the list. And yeah, this just iterates and it works. And as you can see, part one it runs very, very quickly, and part two takes a little bit longer. One idea I had for making this run faster is to use, well, one idea is to just use tuples, because not having to mutate and copy these things, I'm sure, would run a little bit faster. The other way that it could be done is to use something that is much better at appending and prepending items, because lists are very slow at appending and prepending. I remember last year I had to use a B list, a binary list that used a tree to give log-n insertion and deletion, and I'm willing to bet that would cut off a lot of runtime here. But yeah, so this was day 22. If you're curious how I did, I got 445 and 709, and this would have been a lot faster if I'd found that off by one error more quickly. But it is what it is. Part one, it's just a matter of how fast you can get all the code out on the page. But yeah, pretty happy with this. So hope you enjoyed. Bye.